Okay, this session is going to talk about steam tables, just a basic orientation, and then we'll talk about the heat flow equation for steam, and then we'll do some applications and actual examples. If you've never seen the steam tables before, this is a zoomed in version of the saturated steam tables. Now basically, there's a lot of information on here. There's volume and all this other stuff, but for energy purposes, we're primarily interested in the enthalpy. And enthalpy is always going to be in the units of BTUs per pound. Enthalpy has a few different ways it's noted. One is the enthalpy is always the H, and you can see here H sub F is going to be the enthalpy in the fluid state. Okay, now H sub G is going to be the enthalpy in the gaseous state. And often this H is a lowercase h anyway, so this can be written as H sub G like that. And then HFG is basically the enthalpy of the phase change in going from water to steam or from steam back to water. And when you're putting energy into water and you're turning it into steam, the H sub FG tells you how much energy, BTU per pound, you need to put into that water to turn it into steam. And then once you're in steam and you want to go back to water, the HFG gives you the enthalpy in BTU per pound that is liberated when you transfer the steam back into water. So let's take a look at some of these values. You can see at 32, basically freezing, the enthalpy of the water is basically 0. It's pretty linear because it's 1 BTU per pound per degree Fahrenheit. So every degree that you go up, you're going to go up 1 BTU per pound. So if you go to 70 degree water has 38 BTUs per pound, which is exactly 32 points trailing from 70. So it kind of makes sense. It's linear. Now, when you continue to go up, in temperature up to 212, you can see that you have enthalpy here of 180 BTUs per pound for 212 degree water. And if you were to convert that water into steam, you would need to put 970 BTUs per pound into that water, and then it would have a combined enthalpy of 1150, okay? BTUs per pound once it's in the saturated steam state. Now what's interesting about saturated steam is that if you know the temperature or the pressure, you can find the saturated steam, because saturated steam is kind of like steam at 100% humidity. It's right on the line, and so it's somewhat like our psych chart where we're on the saturation curve. There's some physical boundaries there. So if we know temperature or pressure, we can find the saturated steam numbers. So let's take a look. This table is organized by temperature, and a larger view of this is here. So you can see it's organized by temperature going down the page. Nice, even numbers. We can find the enthalpy, given any temperature. So enthalpy of 260 degrees, the enthalpy in the water state would be about 228, and if we turn that into steam, it would be 1167. Okay, so this one is organized by temperature. The next page shows you that the enthalpy is organized by pressure. So if you're given pressure, see this is right at sea level. What's also important to note is this is pressure PSIA, which is PSI absolute. PSI absolute is going to be the gauge pressure plus 14.6. Okay, so given any temperature or pressure, we can find the enthalpy values because they're always going to be in this column here. Okay, and if you need to, you could zoom this in and see these numbers. Okay, so let's review the heat flow equation for steam, which is going to incorporate those enthalpy values. This is the equation. It's very similar to the equations in the HVAC section, although I think the boiler section or the steam tables applications are actually easier than the psychrometric chart because you have less things to deal with, and basically you can get this enthalpy value much easier from these tables than you can from a psychrometric chart. So let's put these into application. Here's boiler example number 1. Say we got 100,000 pounds per hour of 60 degree water is heated to 400 degrees saturated steam. And the question is, how big a boiler do you need? The real question is, what is the Q that is required to get this water to change from 60 to 400? Let's draw a quick picture of what's going on. So here's what's going on. Water's coming into this boiler. This is the boiler here, a cylinder. The water comes into the boiler at 60 degrees, and I'm really simplifying this, and say it's flowing at 100,000 pounds per hour. That means the flow rate here pretty much has to match the flow rate here. Input to output has to be equal. So we get water coming in at 60 degrees and it goes to 400 degrees. The real question is, what is the enthalpy initial and what will be the enthalpy final? Because our equation is Q equals m dot delta H. Okay, so the enthalpy initial, we go back to the steam tables, and let's go find 60 degrees, and the enthalpy is going to be 28. The enthalpy final, let me get rid of some of this stuff. The enthalpy final was going to be 400 degrees, but in the gaseous state, in the steam state. So the enthalpy final is 1201. Okay, so let's do the math on this. Our mass flow rate was 100,000 pounds per hour, and our delta H was 1201 minus 28, which leaves 1173 BTU per pound in delta H, in enthalpy change. So we multiply these together, you can see the pounds cancel, and we've got BTU per hour. Okay, let's do another example. Let's say we take that same steam that we just made at 400 degrees Fahrenheit, and I want to incorporate the pressure aspect of this. We run this through some process, and it comes out as water, and we call water condensate in boilers after it has gone from steam back to water. So we have condensate, and the condensate is at 20.7 psia. Okay, and so again, the question is, how much heat was liberated by the process? So let's take a look at this. Same kind of thing. Q equals m dot delta H, and our mass flow rate is going to be the same, 100,000 pounds per hour. Let's take a look at our H1. Okay, our enthalpy initial is going to be the 400 degree saturated steam, which we did from the previous problem was 1201 BTU per pound. And the question is, what's the enthalpy in the final state? Now we're going to need to go to the pressure tables. So if we look at the pressure table of 20 psi and it's in the water state, it's about 196.27. So basically our flow rate is 100,000 as before. Our delta H is 1201 minus 196, which gives me 1,005 BTU per pound. So just to recap, we've covered how to get yourself acquainted with the steam tables. We've talked about heat flow equations and the enthalpy applications dealing with, temperature or PSIA. And in the SI units, it's basically the same. It's just different units, but it's the same process. Hope you've enjoyed this. Hope this helps you, and we'll catch you in the next section.